All right, let's go ahead and upload these last class, and then we'll get yours going. Alrighty, so where did we finish off last time? We're talking about alkene reactions. Remember, these are not going to be on your exam on Monday. We covered most of them last time. We pretty much did all of our addition reactions. Right, let's see. Yes, epoxides, anti-syn hydroxylation. Yes. Okay. So, in that case, we're going to start today by talking about kind of the last little bit here of our many reaction foray into alkenes, and that's going to be on oxidative cleavage. That last reaction. Okay, oxidative cleavage. We're going to take an alkene. I think this is our typical alkene of choice. We're going to give it. We have two options here of choices of what to make. We're going to see that ozonolysis will be one of them. We are going to cleave our double bond and replace it essentially with oxygens on either side. And so we will cleave our molecule. So this is different from the standard additions that we've been talking about, where we're going to put a substituent on one of our carbons, either the Markovnikov or anti-Markovnikov position. With oxidative cleavage, we're going to be completely breaking that double bond, separating the single bond as well, and replacing it with oxygens. We're going to see that that's one way to do it. We'll look at the mechanism in just a second. Um, if we use high temperature permanganate in either acid or base, but typically acid will work for this, you'll end up cleaving it slightly more differently. And well, we're not going to look at a mechanism for that one, but suffice it to say is that the permanganate, being a stronger oxidizing agent, is going to oxidize your alkene all the way up to the carboxylic acid, whereas the ozone, O3, will get you to the aldehyde. Of course, ketones cannot be oxidized because they are already four bonds to that carbon that are already two carbons or oxygens, so there's nowhere for it to go. We're going to see that oxidation will remove CH bonds. We have no CH bonds in the ketone carbonyl carbon. So we're going to see that these are two ways of cleaving an alkene. So let's take a look at the mechanism. So here we go. With an alkene, this is ozonolysis, ozone breaking, lysis breaking ozono for ozone, of course. So we're using ozone to break our molecule apart. And if we remember ozone's Lewis structure, let me move this down just a little bit. Ozone's Lewis structure, of course, it's resonance stabilized, right? We're going to see that we're going to have it come in to our molecule, and we're going to kind of make this five-membered ring here. We've got basically now three oxygens and our two carbons in a five-membered ring. And we're going to do a kind of rearrangement there, which ends up leading us to having the following. So there's just a rearrangement that happens. You end up technically breaking one of these oxygen-oxygen bonds. You don't need to worry about the rearrangement, but it just rearranges the bonds here. So we still have our three oxygens and two carbons as part of this ring. And once we have that, this species is called an ozonide, by the way. So is this. Once you rearrange to the second ozonide, that's when we have our reducing agent come in and it'll start cleaving things. So our reducing agent is going to cleave these bonds here. So in the presence of a reducing agent, such as dimethyl sulfide, I'm going to do DMS in a different color. There are other ones you can use. You can use other reducing agents like zinc, but this is the most common one. This thing, by the way, I'll write it out. This is dimethyl sulfide. This is a reducing agent. And what's going to happen is we end up cleaving our substrate, giving us the aldehyde plus the ketone. No R's, they're both methyl groups here. So we get the aldehyde and the ketone. All right, and then technically we also get dimethyl sulfoxide. So notice we had three oxygens in our ozone. We end up with three oxygens in each of three molecules, or one oxygen in each of three molecules, giving us three oxygens overall. So that's where all these oxygens end up going. Of course, DMSO is a solvent. We can go and use it and do other things with it. The aldehyde and ketone we can isolate and then do whatever we need to do with them. So suffice it to say, you take an alkene, treat it with ozone and a reducing agent like dimethyl sulfide, and you'll end up cleaving your alkene, producing an aldehyde or and a ketone or two ketones or two aldehydes. It just depends what your double bond is. So suffice it to say, you just take, a good thing to do is count your carbons. We're going to do some examples of these, don't worry. And then make sure that your carbons at the end still are the same. For example, on the left side of the double bond, we had two carbons. So one of our products should have two carbons. And on the right side, we had three carbons. And so we have the three carbons there. So it's always a good idea to keep track of your carbons. This is a good way for me to trick you as well. Because I can, reverse the products, and now you have the ketone on the left, the aldehyde on the right. You're like, what's happening? Um, just keep track of the carbons. Always a good idea. So, and then if you use the permanganate instead, just be aware that instead of an aldehyde, you will end up with a carboxylic acid if you have only one substitute on your double bond there. So I'm going to write it in blue. This also oxidizes the aldehyde to the carboxylic acid. That's something we'll focus on later on. We'll learn about oxidation later, but just accept it for now, I suppose, that if you use ozonolysis, it's a little bit gentler. You end up with ketones and aldehydes, some combination thereof. If you have KMNO4 with that's hot and acidic, you'll end up with carboxylic acids and ketones only, no aldehydes. Interestingly enough, if you take something like this, just a disubstituted alkene, if you do ozonolysis on this, you'll end up with your ketone, and you'll end up with formaldehyde. If you take that same alkene and treat it with the KMNO4, that's hot and acidic, you end up with carbon dioxide. You're going to end up oxidizing it to carbonate or carbonic acid, which will then dissociate. So if you remember way back when, we were talking about double displacement reactions in Gen Chem. And remember that if you produce carbonic acid as a product that we saw that CO2 was produced, we saw the bubbles, right, that come out when you make carbonic acid. So it's the same idea here. Still in OChem, you have to worry about your double displacement carbonic acid decomposition into CO2 and water. Yeah, so technically you'll make water as well. So you'll end up getting all this stuff out with your KMNO4. So just be aware that you do not get aldehydes with the permanganate. You'll only get ketones and carboxylic acids. This part here together is carbonic acid, right? CO2 and water is carbonic acid, which would be the equivalent carboxylic acid of formaldehyde. So just be aware of that. However, if you have both sides having two substituents, doesn't matter which reagents you use, you'll get the same thing. You'll get two acetones out from this. Doesn't matter which one. So ketones are always there if you have carbons that have that. And then just be aware of which oxidizing agent you're using. If you're using ozone, you get the aldehydes. If you use permanganate, you get acids. And in the case of carbonic acid, it produces CO2. So it bubbles away. And off it goes. All right, so that's all of our alkenes. That's all we have. Let's take a look at some examples, shall we? Let's take a look at some examples of these. So let's do ozone and DMS with this. So let's take a look at what's going to happen. We're going to see that we're going to cleave all of our double bonds, no matter how poorly I've drawn them. We're going to cleave those double bonds. And we're going to replace everything with oxygens. With ozonolysis, if we are producing an aldehyde, we leave it as the aldehyde. So we can go ahead and do that. If we do this, the top half of the molecule becomes this diketone. And how do we know that? Well, we had 1, 2, 3, 4, 5. And we had the double bonds on carbons 2 and 4. And so we see that those two carbons, 2 and 4, will now have our ketones instead. And if we take a look at the bottom half of the molecule, we have 5 carbons there with alkenes on carbons 2 and 4. And so we end up with the same molecule upside down, but that doesn't matter, of course. So we really get two equivalents of this same molecule, this this pentane dione. Although you don't know how to say that, but you get the same molecule. So in this case, so it's simply a matter of separating your molecules, replacing everything with oxygens as necessary. If we take a look at something like this, if we treat this with ozone, we're going to cleave all of our double bonds. And so it's important that we keep track of what's connected to what. So we have 1, 2, 3, and these numbers aren't for naming or anything. These are just arbitrary numbers so that I know how many carbons are in my final molecule. So in this case, we're going to end up with something with 8 carbons, as well as something with 2 carbons. And the reason that we're going to see this is because notice that we have, in the previous molecule, we had like complete cleavage, right? 2 and 4 on either side were both getting completely cleaved. So I'm only numbering things that aren't, I'm numbering things that aren't part of that cleavage, if that makes sense. So if we see this light blue numbers from 1 to 8, those carbons are still together. Those bonds are not being cleaved. So we're going to see that on carbons 2 and 7, we're going to end up with an 8 carbon molecule. So 1, 2, 3, 4, 5, 6, 7, 8. On carbons 2 and 7, we have an alkene or on that thing, and then on carbon 4 as well. So 1, 2, 3, 4, 5, 6, 7, 8. So on carbons 2, 4, and 7, those are ones that previously had alkenes. Those are now going to have ketones. So carbons 2, 4, and 7 have our ketones. And then we also have the second molecule, which is just 2 carbons, and that molecule will just be that. So it's an aldehyde. And if we want, we can draw the H. Usually those are drawn with aldehydes, but it's not necessary. If you leave it as just the way I drew it a second ago, that's just fine. And so in this case, carbon 1, that's what I've arbitrarily numbered it. So it's important that you count your carbons and keep everything that's not being broken together. So you might be tempted to have carbons 2 and 7 on separate molecules, but they're not going to be on separate molecules because there's no other cleavage that's happening between carbons 2 and 7 in that ring at least. So that's the idea behind this. And then if we have something crazy like a bicyclic system, we love our bicyclics. If we treat this with ozone, we are going to cleave this thing. Let's keep it, let's look at what we're doing here. I'm going to number the carbons of our ring, because we are going to have a ring. That's our main parent here. And then we're going to have 2 carbons outside of that ring, which I'm going to number 6 and 7. And 6 and 7 are going to carry the double bonds. So the ring from 1 to 5 is not being broken. That ring is staying here. But the second ring of this bicyclic system is being broken. So we're breaking the ring that's 2, 3, 4, 7, 6. That ring is being broken. So we're going from a bicyclic to now a single cyclic. So I'm going to we're going to have 5 carbons in a ring. 1, 2, 3, 4, 5. And then on carbon 2, I have carbon 6, and on carbon 4, I have carbon 7, and both of those are going to have double bonds to oxygen. And notice that these had hydrogens before, so they still have hydrogens. They're going to be aldehydes. So it doesn't really matter what numbering system you use for these, but just make sure that your answers, all the carbons are accounted for. I'm going to separate this a little bit, just so we don't think that that purple part is for this problem. All right, so do we see this? So we had our bicyclic system. It broke one of the cycles, and now we have two aldehydes that are two carbons away from each other, and we'll have that. And if we wanted to be really careful about this, we wanted to be very, very good chemists, you would actually have drawn it with stereochemistry. Keep my two there. We would keep the stereochemistry as well. So, fun. And it doesn't matter if it's this is a meso compound, right? So it can be the wedges or the dashes. I don't want to put plus minus because it's not really racemic. It's meso, so it's not chiral, but we do end up with a single enantiomer. I'm sorry, a single diastereomer. We don't get one wedge, one dash in this case, because if you look between carbons 2 and 6 and 4 and 7, they're both pointing down away from that five-membered ring, right? So they would still have essentially syn stereochemistry to each other. And so it's meso, so it's not chiral, so we don't really have an enantiomer for it, but um, this is the only set of stereoisomers we get. We get this and the wedge one, which is meso. So either way, we're good. Cool. So stereochemistry is still a factor here. So don't ever forget that. Will we have any other stereochemical considerations? No, we don't have any other chiral carbons in these. So fun. All right. Let's see here. All right. Let's kind of summarize. What to do about alkenes. If you're trying to predict the products, we're going to look at this under a couple of different lenses. The first one is going to be in the lens of predicting the products of a reaction. Um, and so you first off have to see what's happening. What set of reagents are you given? What's expected to happen? You're expected to figure out what transformation is going to take place. I.e., is this an addition or is this a cleavage? If it's an addition, are we adding a halogen? Are we adding a hydroxy? Are we adding something else? So it's important that you understand first what transformation should be taking place with your reaction. So example, if you're given Br2 in water, The transformation that's associated with that is that you're adding a hydroxy group and a halogen. You're making a halohydrin with that set of reagents. So the first thing that you want to analyze is with a set of reagents, what are you even doing? What are you going to be doing with those reagents? What are you adding to your molecule? Next, we need to think about regiochemistry. And that's going to be, is this Markovnikov, anti-Markovnikov? So we have to consider what's going to happen with halohydrin, right? We're going to end up with a Markovnikov hydroxy and an anti-Markovnikov halogen. So it's important that we understand which position within the alkene we're reacting, or if we're having uh, different things happen to different carbons, or something only happening to one carbon. It's important if we know the regiochemistry of this. So are we ending up with a Markovnikov addition or an anti-Markovnikov addition to our stereochemistry? And thirdly, we then need to we need to consider stereochemistry. And that's going to be, is this a syn or anti addition? So if you can answer these three questions by after being given a set of reagents, you'll know what to do. If your set of reagents is, say, cold basic KMNO4, first question is what transformation is taking place? For cold basic permanganate, this is an addition reaction. We are adding two hydroxy groups. Regiochemistry is irrelevant because we're adding a hydroxy to both. So not applicable here. And then this is a syn addition. And so if you understand this, you can take it to any alkene that I want to give you. Say we do the same one we just did the other bit for. We're adding two hydroxy groups. Doesn't matter to which one because we're adding it to both. And we're adding them syn to each other. So if we are to take KMNO4, cold basic, to this molecule, we're expecting it to add two hydroxy groups to each alkene. And they're going to be syn to each other, so they will have the same stereochemistry. Now, of course, there's no reason we're going to get a couple of diastereomers here as well. We're going to see that we have as well other one. All right, so we're going to get four different isomers out of here, but the point is that they're syn along the alkene that used to be there. So you're going to end up with either they both happen to be syn on the same side because we have two alkenes, or one is syn up, the other is syn down, or vice versa. So you'll end up with four different stereoisomers here, even though you have four chiral centers, so we would expect 16 potential things, but we don't have 16. We only will see four. So there is a great deal of stereochemical consideration to take place here. So hopefully we can see why we get these two as well as their enantiomers. So we have them, they have to be syn to each other, right? The alcohols that are put on However, the other alkene can do syn whichever way it feels like. If the left alkene decides to do syn wedge, the other alkene could do syn wedge, giving us the first product, or the bottom one, which would be syn dash. So either way, we're good. We make both of those. We would expect probably an equal ratio, 1 to 1 to 1 to 1, of all of these four isomers. They could both be on syn dash. They could be the opposite. So you end up with 4 isomers out of, so the other 12 do not form with this reaction. All right, so stereochemistry is still relevant, and I expect you to put plus minus indicating racemic on as the stereochemistry for your molecules as necessary. So don't forget that. All right, so I don't want you to say, I'm gonna put it in red. Don't just be lazy. Only I'm allowed to be lazy. Don't just say this. That's not even the right way to put OH, but don't just do this. There we go. Don't do this. Wrong. That only answers question 1. You have to know 3 things for every alkene reaction. You have to know what's happening, where it's happening, and what stereochemistry do you get out. Those are the 3 things you need to know. So I would expect on this, if I were to say, take this molecule and predict the products given this reaction, I would expect you to draw both of these things along with the plus minus to indicate that it's racemic. So on your homework, you should be doing this as well. Do not forget your stereochemistry. And of course, sometimes if a particular reaction is putting one thing on, we're going to see a mess of stuff can happen, and I'll try to avoid those. Like this, we have 2 products that are racemic. Not a problem. You can draw both. I'm not going to give you one that has like 8 different stereoisomers that you're going to have to draw, so don't worry about that. All right, so it's simply a matter of, I say simply, understanding your reagents and what they'll do to your molecule. And then later we'll look about synthetic strategies here. Let's take another example. So you should do this for all 14 of our reactions, or I guess we're doing 13. However many we're doing, let's see it. So how about this? What does this set of reagents do? Well, we've got to consider, what is this going to do? And so pause the video, think about it, write out your answer. This is alkoxymercuration, demercuration. And so what happens with this, to answer question 1, what is happening? You're adding a methoxy ester and a hydrogen. Where are we adding these two? This is a Markov-Nikov addition. So we are adding OMe via Markov-Nikov's rule to the more substituted carbon. So I'm going to just write that. This is a Markov-Nikov addition. And step 3, what's the stereochemistry here? This will just be racemic. But technically, this will be a syn addition, right? is a syn addition, although because we're adding hydrogen, typically that's not going to make the other one chiral. But sometimes it might. So it's a syn addition here. All right, so let's take a look at the same thing. Although this one's going to be a bit more complicated. This one will have more products than I would want to give you on your exam. And unfortunately, we can't just put plus minuses everywhere because one plus minus means the whole molecule. You can't just say for this chiral center it's plus minus. Wouldn't that be nice? So if we're adding OMe according to Markovnikov's rule, we have two different regiochemical outcomes that are going to come out here. In either case, we're going to get our OMe here, but we could get the OMe on this one. So this is when you're going to end up with 4 different isomers. Again, that H doesn't really matter. So that's one isomer. We have the one where they add to opposite sides as well. So we have that isomer, and then we have the different regiochemistry because that left alkene there, the one with is equivalently substituted, right? There's no reason that the top carbon or the bottom carbon is better suited to be reacted. So we're in fact going to get 4 products out of this, as well as their enantiomers. So the one that I said we're going to get 8 enantiomers out of, and you didn't have to draw them all, this is just an example of that I don't want you to have to draw so many freaking isomers. So this one, of course, would be just the down because the hydrogen goes wedge. And then we have that isomer. And then finally in lighter blue, we're going to have the last one, which is where we have that. The other one. So we have 4 isomers. The reason we have 4, of course, we have the same sort of addition we had last time where they can be adding to the same side or the opposite side as each other. Within the reaction itself, along that alkene, it's always going to be a syn addition. And if I were to be a good chemist, I would technically have to draw these as dashed methyl groups, which I will do now. But of course, because there's no, they're both equivalently Markovnikov positions on that leftmost alkene. I can attack either side. So we're going to end up with 4 products as well as their enantiomers. So a total of 8 stereoisomers here. Yikes. So we do end up with a mess. All right, but so this one I'm not going to ask you to do something like this, hopefully. And so we don't have to worry about this sort of thing. This one, yes, you've got to draw both. Got to draw both. With something like this, I'm probably not going to give you, but if it's on your homework, go ahead. Do all of the stereoisomers, and then you can put racemic for each one as necessary. So don't forget your stereochemistry. Right, so unfortunately we get a lot of mess when we have multiple alkenes. All right, and of course it can be simpler. You can do something, you can do a simpler one. Say we have our favorite bicyclic system from before. Here it is. Let's now take, let's do another set of reagents. What shall we do? How about this set of reagents? All right, we've got to figure out what these do. What do these two reagents do? They make an epoxide, which then breaks into two alcohols, two hydroxy groups, we'll say. Regiochemistry is not applicable because they both will get a hydroxy. And then this is an anti-hydroxylation. So we're going to have them anti to each other. Our hydroxy groups will be anti to each other. So if we understand that about this set of reagents, we can go ahead and we lost carbon. If we do that, we just need to say, well, what's going to happen to this molecule? Thankfully, this is a relatively easy one since we're only doing one addition. We're going to erase our double bond. We're going to put on two hydroxy groups that will be anti to each other. Plus, minus, done. There's no reason to choose one over the other because, again, stereochemically, we just need them to be anti to each other. And while this molecule is completely symmetrical anyway, we're going to see that there are ways to make enantiomerically selective epoxides called the sharpless epoxidation. That's something we'll cover next semester. So for right now, we get a racemic mixture. Hooray. So it would be a very good idea for all of the reactions we've learned for you to take a look at the sets of reagents, figure out what they do, where they do it, and what's the stereochemistry. Though if you can answer those three questions, all you have to do is erase your double bond, stick those things on, and you're done for predicting the products. So you'll want to do that for all of your reactions. So let's take a look at some examples. I mean, you have so many on your homework, though. I'm going to leave that for your homework. So go ahead and focus on doing your homework. Make sure you're doing these multiple times because, again, multiple sets of practice. And if you want, take a single alkene and do all of the different things to it. Do your 13 reactions on it. See what you're going to get and where. The more you practice, the more you're going to be able to internalize all these things. And so, also, it's important that we don't get confused because if I were to change this to, say, like this one, I can change this to ethanol. And instead you add an ethoxy group. So just be aware that there are some generic, things you can do. Like you can put an R group on. Doesn't matter what your R is. Ethyl, isopropyl, methyl, whatever. Hydrogen, have water added, you're going to have a hydroxy instead. So just be aware that Don't fall in the hole of thinking this has to be methanol. No, you can use any alcohol, you can use water for this reaction. The only thing that changes is that R group. And so your reaction does the same thing. It's still a Markovnikov addition. That's a syn addition of hydrogen and an alcohol, or if not an alcohol, then it's uh, an alkoxy group, so an ether. So lots of things to do here. And so don't get stuck on that either. So just be aware that multiple variations of these reactions can exist as well. All right, let's look at some synthetic strategies. Look at synthetic strategies. Not reactions, but strategies. I might also ask you, how might you get this? Predicting the reactants now. Actually, let me do that before we talk about synthesis, because synthesis will be a different monster. What if you need to predict your reagents? Thankfully for us, we'll talk about synthesis later. With your predicting reagents, meaning you're given an alkene to start and then your product, if you need to predict the reactants necessary to make that happen, it's again the same thing. Number one, what happened? What transformation took place? Did this become an alcohol? Did we add an OH to the molecule? Did we add a Br to the molecule? Where did it take place? And then the stereochem. So if you think, okay, well, here's our starting material, and we do not know. Here, I'll let's use chlorine. I feel like we've used bromine too many times today. So, what's going to happen with this? We have to think what took place. In this case, we have added a halogen and an alcohol. Number two doesn't really matter because we have symmetry here. Our starting material is, there's no Markovnikov or anti-Markovnikov position, although we would have that with this particular reaction in other cases. Um, and then the stereochemistry we see is anti, right? We see that this is an anti process. So if we can figure out these three things, then we compare it to all the work we did for the previous kind of section we talked about, which was, defining your set of reagents to accomplish X, Y, and Z. If you identify a set of reagents to get these three things done, they'll see, well, this is Cl2 and water. Cl2 and water gives us these three things. In theory, number two would be that it would give us a Markovnikov water hydroxy and anti-Markovnikov halogen, although that is not applicable here because we don't have those positions. But if we did, here, I'll make this easier for us. There we go. So we see that we've added Markovnikov hydroxy and we've added an anti-Markovnikov chlorine. So that's halohydrogen formation. So that's Cl2 and water. Interestingly, what if I did this? What if I wanted the other one? And of course, I mean, for this one, I don't have to tell you. I mean, yes, it's plus minus fine. Um, although, no, I'll leave it at that. Okay, let's take the same molecule. Whoops. What if I had this one? Well, we'd have to think about it. Okay, well, we've added same thing, Cl and OH. We have a Markovnikov Cl, an anti-Markovnikov OH. They're anti to each other. What the heck? What are we going to do here? We have technically a halohydrin, right? But this is a tricky one. This isn't the normal stereochemistry we're used to seeing, or rather regiochemistry that we're seeing with halohydrin, right? We're used to seeing it completely different. So what's happening here is this is going to be an epoxide and a nucleophile, right? The epoxide will end up giving us the anti-Markovnikov hydroxide with this. So this will be MCPBA or just RCO3H, whatever, that's okay too. And our second set is just Cl, NaCl. So we're doing an SN2 type pop it open, and there we have it. We're doing an SN2 type of reaction there. So here's a solvent for you, if you like. We have chloride as a nucleophile come in. It opens up our hydroxy group, and we're going to end up having that there. Technically, because our product is protonated, we're also going to need an acid wash at the end. So don't forget that too. Because if you just put NaCl with an epoxide, you would get this. You would end up with the salt of it. If you want that to be a protonated one, you've got to use either water or acid. And acid is usually a good choice for this. So keep that in mind as well. So don't forget, if you have alcohols, you've got to protonate them somehow, generally speaking. And so you'll need some sort of proton source. So don't forget that as well. All right, so this chapter has a ton of info, a ton of reactions, a ton of things that can take place. And there's three things you have to pay attention to: what happened, where it happened, stereochemistry. And if you want to think, what if they were sin to each other? Nah, I'm not going to be that mean. I could be that mean. By the way, interestingly enough, if we didn't have that pesky methyl group there, both sets of reagents would give us the same. Ooh, I'm hesitant to say this because it's a bicyclic compound. Um, uh, Never mind. Let's. Uh, if I wanted the sin one without that methyl group, Look at how mean I am. What if I wanted the sin version of this? If I wanted them to be sin to each other? And let's put a CL on this. We'll make it a little bit easier on ourselves. So this is added. We've added those two groups. We have no more Kovnikov positions, so not applicable here. And then our third one is that they're sin to each other. And we don't have a set of reagents to do this. We do not have anything to directly make a sin halohydrin. We don't have a set. So this tells us that multiple reactions have taken place. We've not done one thing to this molecule, we have done multiple things. So we have to think, how might we get this to happen? Well, how might we get this to happen? Well, we do know how to make the anti version of this. And we think, okay, well, we don't know how to make a sin one, but we know how to make the anti one. Well, is there a way to go from anti to sin? There is, right? If we had something like this, we can just do an SN2 reaction on it afterwards. Once our bromine is on there, we can just SN2 it. And poof, remembering that SN2 inverts your stereochemistry. So that bromine position, and notice I'm using bromine because chlorine is a better nucleophile than bromine. So although this is technically going to be an equilibrium reaction, uh, the bromine is a better leaving group than chlorine is. Chlorine's a better nucleophile than bromine is. So we're going to be able to switch that out here. So it's nasty. Look at all the nasty stuff I can do. We can say, aha, well, if we do Br2 water, we can get that anti halohydrin. And then if we just do an SN2 on it, we can get the syn halohydrin. So don't forget your previous stuff. This is how nasty organic chemistry gets. And think we've learned 14 reactions now, plus 4 reactions previously. You have 18 now. Just wait. Till the end of next semester, you're going to have hundreds. And yes, you need to know them all. It's really nice. I get to torture you guys so much with this. So don't forget your previous stuff. Okay, that's important. So, because if you forget your previous stuff, then you're going to be really limited in what you're going to be able to do synthetically speaking. So, predicting the reagents is important. Something like this, it would be harder to predict the reagents for, but you could do it. Let's talk about synthetic strategies, because that's kind of what this is talking about. So synthesis is going to be multiple steps. And unfortunately, you're going to have to take into consideration. I'm sorry, we don't have only uh, 18 reactions, we have 20. right? We covered two other reactions in our radical chapter, right? We talked about halogenation of alkanes. And so, like, I can basically give you, like, here you go, take this butane and make for me this molecule. Meso, of course. But make for me this molecule. This is a synthesis. I'm asking you to make something for me. And I'm just going to move it down just a bit so it's not there. So when it comes to synthesis, generally we do this backwards. We analyze our product and then figure out ways to make it, and then see which one our starting material can fit with. So we analyze, we see, aha, this molecule, this product, has got anti-halogens on it. I'm sorry, syn-halogens on it. Do we know a way to do, this will be, I want to start with the simpler one. Let's start with anti. So we have anti-halogens. It'll be a little bit easier. We know how to do anti-halogenation, right? Anti-halogenation, not anti as in the opposite of, but anti as in opposite sides, one up, one down. We know how to do that. That's an alkene plus your halogen. And so we have to think then, what alkene would give us this? Well, we know that anti-halogenation puts bromines across a double bond. So therefore, the double bond that must be present before this must be this molecule. So we're going to work in reverse. This is called retrosynthetic analysis, and is arguably one of the more important and hardest to develop skills of organic chemistry, is looking at things backwards. Looking at your product, how can I make this? Well, we know how to do anti-halogenation. That's just bromine and an alkene. So we then have to ask ourselves, okay, well, this is the alkene that we can make into our product, but now how do we make this alkene? And we go back and we think, okay, well, how do we make alkenes? Well, to make alkenes, we have a couple of options. We could dehydrate an alcohol. We could also eliminate something that had an alkyl halide. And looking at our starting material, we don't see an alcohol there, right? So it'll be a little bit tougher for us to justify dehydration of an alcohol to make the alkene. So what about an alkyl halide? Probably a good idea. If we eliminate an alkyl halide, we can do that. And this is just an elimination. We can do either SN1, I'm sorry, either E1 or E2. Probably better to go E1. The reason being is that we want the Zaitsev product, right? That's what we're looking at here. So let's go E1. So our reactants then are going to be a good base, protic solvent, heat. That is going to end up eliminating our halogen. And now we have to think, how do we halogenate this? How do we go from our starting material to this alkyl halide thankfully this one we do know. We just do radical halogenation of our alkane, and then we can do all this sort of fun stuff. So we're able to look at this, figure this out working backwards. That's generally the best way to go. It's tempting to go forwards because that's how we've been trained for the last 20 years in the educational system: is start at your starting point and end at your ending point. But it's really more useful for us to start at the end and work our way backwards. And so by doing that, that'll generally give us a more clear answer. Because it's like, if we start at the beginning, we can do all sorts of things. And now that we've made the alkyl halide, now what do we want to do? Do we want to try brominating again? Do we want to... I don't even know. Do we want to do an SN2 on this bromine thing? Like, you got to make your choices, right? So it's a little bit easier to work backwards because you know where you're headed. And so you have to just think, how can I get there? And so it's all about the process of analysis. So let's do another one. All right, let's see if the book has any good analysis problems. Ooh, here's a fun one. Yes. All right, here's another synthesis problem. This is a synthesis problem. And I mean, I don't have to start at the OH. I could give you the alkane, and you can go ahead and do the rest. But let's see how the heck we're going to do this. So, how do we make an alcohol like this? Always start at the end product. We're making a primary alcohol, an alcohol that is on a carbon that is two hydrogens on it. So we have to think, how do we make a primary alcohol here? We have a primary alcohol. Well, let's think, how do we make alcohols in general? We have quite a few ways to make a single alcohol. We have hydroboration oxidation. We have oxymercuration demercuration. We have acid catalyzed um, hydrolysis of alkenes. And so we have three different ways. And so we have to think about it. With those three ways to make the alcohol, if we do the acid catalyzed one, that forms a carbocation, which we're going to end up having be on the tertiary carbon there. So it's not going to make a primary one. So that one's out. How about oxymercuration demercuration? That would be a Markovnikov addition, but we're clearly on the less substituted of two carbons. So we're not looking at a Markovnikov, we're looking at an anti-Markovnikov one. So we're looking at an anti-Markovnikov hydroxylation. And so we think, well, I know how to get there. Well, why don't we just start at the alkene and use the hydroboration oxidation to do that. All right. So now the problem is, how do we get this alkene? We know how to make the primary alcohol, and the only way to make this primary alcohol that we have learned would be to do hydroboration oxidation. I mean, yes, in theory, you could take that, if there was a bromine on that position, you could, if there were a bromine on that position, you could do as SN2 or something, but little bit that's a little harder because then you have to go from alkene to bromine, then to SN2. So you're adding more steps. So it's also important that we are efficient with these processes. If there's a way to do it in one reaction, that's better than doing it in three, right? If you can do the same thing in three reactions, but you can do the same thing in one reaction, choose the pathway that's one reaction. Always faster is better. So this alkene, how are we going to make it? Oof. Well, we see here this is a Hoffman alkene, right? The Hoffman product. So that probably came from an E2 reaction. So conditions for that would be something that has, you could either have a leaving group, you could have a leaving group on either, no, it's got to be the leaving group on this one. Gotta have a leaving group there, and then we'll have our bulky base come in and grab a hydrogen off. Right, so that's going to be, say, T-butoxide, and I don't know, DMSO, let's say, some solvent, whatever you choose. All right, so how are we going to put a leaving group on there? Well, we have an alcohol originally. Is there a way to make an alcohol into a leaving group? And yes, there is. And that leaving group would be the tosyl. So all we need to do is put our tosylate with, I don't know why I put one, put these together. Tosylate this lovely alcohol with your pyridine and your tosyl chloride. You make the tosylate. Tosylate can be eliminated, giving us the Hoffman product. And then you can do your hydroboration oxidation. So that would be the pathway from getting from your starting material to the end. And again, we started at the end and we worked backwards. So we know we needed the alkene. How did we make that alkene? Through elimination, that would give us the Hoffman product. So we needed to do E2 on it. Remember, E1 will give us Zaitsev. Zaitsev is not what we wanted here. We wanted the Hoffman product, so then we could anti-Markovnikov hydroxylate it. By the way, this OTS, I've drawn it up. That's really the same as drawing it down, right? There's no difference. So I can do that if it makes you more comfortable, but can't be comfortable in OChem. I could throw this molecule to the side. What if I did this? Like, how mean would this be? Like, I could go crazy. It's the same molecule, just rotated, right? So, like, as I had before. So, don't be scared. Always count your carbons. Keep everything the same that used to be the same. There may be rotations involved. That's just me being mean. But, if I do that and say, okay, well, you might think, well, the OH has moved all the way to the left carbon. But you gotta count them. And it doesn't matter, again, which numbers you use. Just be consistent. We know that carbons 1 through 5 are connected in a line. If I try to do that, so that's clearly not going to work. So carbons 1 through 5 haven't really changed. They're still there. I could say that this is what we have. I could start numbering on the bottom. It doesn't really matter. As long as you are consistent with your numbering scheme, you can see what's happening. Well, carbon 6 has the alcohol used to be on carbon 3, now it's on carbon 6. and then you can think about it. And then if you want, you can redraw the product so that it is closer to what the reactant was, and that might help you visualize it. So there's so much to think about with these, and it's fun. So for me at least, there's giant puzzles to be done with these. Um, I have some suggestions as well. Let me hop over to some of the stuff on our Canvas page. Oh my gosh, I have to log in and everything. Why is it like not automatic on this one? Okay, let's take a look at some of the stuff I have for us here. So let's switch over. Nope, I have to make a new screen. Okay. If we go, I didn't give us the NMR Labster. Okay, I'm gonna make that active and I'll give a due date on that. Shoot, I meant to give those a while ago. Okay, oh, and I didn't give you any for the electrophilic additions either. Look at all these we have. Okay, that's good enough. I'll make those due at some point. Um, Synthetic problem set. Looky here what we've got for you. All of our fun reactions. Here we go. All our lovely reactions are there. Um, we have a couple that we haven't covered, like the Simmons-Smith, um, the Grignard reagent. We haven't formed that either. These last two are more for alcohols, so this is going to cover everything through the rest of the semester, including alkynes, as well as alcohol reactions. So we'll deal with those later. But we're going to see that all this information is in one place. Uh, we have a lot of fun things we can do here. So starting with alkanes with 4 carbons, or cyclohexane, try and take a look at some of these. Of course, right now this is intended for the end of the semester, but some of these you can do. Um, Not with 4 carbons, actually, because we haven't learned enough carbon-carbon bond forming yet. Okay, never mind. Well, look what I have for you. Everything in the same place. Yay. Okay, so we actually have to learn alkynes before we can actually do that next part. But we'll take a look at that starting on Wednesday. But these are synthetic problems for you. It's super, super valuable to practice these because not only are you going to learn the plain old predicting the products or predicting the reactants or predicting the reagents used, but you're also going to be combining them, and that's going to help you to learn it. So that's way down at the very, very bottom. So we'll have that as well. Um, so yes, we'll get through with those. So apparently I've not graded your homework before, so I should really get on that. Oh my god, and who has done this? I think we all know actually who's done that, but we'll get to that later. So let's hop back over here. Um, it's an important bit here that we want to focus on. The book has quite a few problems of synthesis. Um, let's see. Do we want to do any more? Yeah. Okay. Let's do one more problem. This is a mechanism problem. Are y'all crying yet, by the way? Oh, hold on, my tablet has frozen. Oh, and now it's disconnected. Maybe that is the it for the end of today. Let's see. We good? You connect. Okay, hold on. Let me try one more time. If it's not connecting, then I guess we're done. Okay. Yes. Connect. Oh, it actually closed the program on me. Wow. Thanks, Windows. All right, we're going to try one more time. I lied. All right, here we go. Are you going to behave? Yes? I think we are, in fact, behaving. Yes, we are. Okay, good. Um, Here we go. This is a problem from the book. The presence of BR2. Fun. CCl4, just a solvent. Carbon tetrachloride, just a solvent. BR2, though, we know what BR2 will do. We know what BR2 will do to this molecule. So, if we want to do that, if we're doing a mechanism, we have to show all of the steps, right? So we know that when bromine comes in, we end up with our cyclic bromonium. So that's the first step in this. Okay, and now how the heck are we going to get to the product? Well, we can have multiple things happen, and it can be, because this is a mechanism, you can do it in many different ways. You can have your bromine come in and attack the bromonium. That works. Or we have an intramolecular reaction that can happen. We can in fact have this hydroxy group bonk this thing open. Remember, it would attack the more substituted side. And this is enough carbons away that it can do it. If you're only like 1 or 2 carbons away, yeah, not going to happen. But there are quite a few carbons away. We have 5 carbons, and then the sixth one is the oxygen. And we know that our product has a 6-membered ring, and one of those members is an oxygen, right? And so, if we do this, what do we end up with? I'm going to just draw everything here. We have one. We have now an oxygen connected to this as well. And we have now the rest of the molecule, the 1, 2, 3, 4, 5 parts of that. 1, 2, 3, 4, 5, 6. That oxygen still has a hydrogen on it, so it is positively charged. The only thing that needs to happen is that needs to go away so we can have something come along, say a bromide. Bromide is not a very good base, but this is also a very unstable acid, so that could work out. And by doing so, we'll end up with our product. So remember, it's scary when it's rotated, right? So we see this oxygen business, we see this bromine thing here. How are we going to reconcile these? And if you wanted, by the way, instead of just reacting your alcohol with the bromonium, you could have had the bromide come in and then do SN2 with your alcohol later. That's fine. That would technically, I mean, we don't have the stereochemistry shown here of what that should be. That would give us clarity if the oxygen is supposed to be anti or syn to the bromine. But since the bromine is not chiral, there's not really one way to prove one or the other. So that would be an example of a mechanism that you could do. So this is an intramolecular reaction. We have the bromine coming in. We make our bromonium. Bromonium has electrophilic carbons on it, which can be attacked by even not so great nucleophiles. And we can go ahead and get that to pop on. And so as a result, we can make our product this way. So lots of stuff to practice. Don't forget about it. Alrighty, I think that's good for today. So I'm going to go ahead and upload these, and we'll stop there. So, all right, next time, not going to focus more on the synthesis. That will be for review sessions. Ooh, big news. Um, Kevin has agreed to host review sessions for you guys on Saturdays. I think it's from 2 to 3, if I remember correctly, and so I'll make that announcement so you guys can have that. He'll just be kind of going over stuff. So go to him with questions. If there's really some like super confusion and he doesn't know what to do, you can then ask me after the fact. Let's shoot me a message and be like, hey, we were stuck on this or whatever, and I can help out as well. Although I may not be available right at that very moment, but it's a good idea. Just practice together. Um, I would definitely, if you can, suggest attending those. So, okay, so I'll make that announcement as well, and we'll go from there. Cool. Alrighty. Well, have a good day, everybody. Keep on studying. Um, get your spectroscopy and radicals really on hand there, and then you'll do awesomely on the next exam. Alrighty. Awesome. Take care, everyone.